The next topic we will discuss is about recovering from failed disk operation. Specifically, we will talk about a condition after your disk failed to write data to your disk blocks. Failure to write the data correctly can be caused either by a loss of power in case you have like a local file system, or loss of network connection in case you have a remote file system. By now you should understand that your file system keeps 3 different data structures in your disk. The first one is a tree of your files and directories, and the second is a list or trees of data blocks, and the third is a list or a tree of index blocks, assuming that index block allocation is the best among the other allocations. And these 3 data structures are referenced from a special place in your drive. For Unix or Linux file system, the special location is the suprablock. Any updates to the file system must update the 3 data structures. If one of them fails for some reason, then your file system will be inconsistent. We will use Unix or Linux file system as our example, but the concept applies to other file systems. Let's say you try to write a file to your Linux file system. The first step is to allocate new data blocks for your file. That means the file system must update the suprablock because the suprablock has a reference to the list of 3 data blocks. And next, the file system must allocate a new inode block, and the list of inode free blocks must be updated from the suprablock as well. And the content of your file will be written to your data blocks, and then finally the inode block will be updated with the metadata of your file, like the owner, the date, the size, and so on. So when any of these sequence is not completed correctly, then your file system will be corrupted, or your data is partially written to your file. To implement reliable file systems that guarantee good data recovery, we will borrow ideas from database transactions. A DBMS guarantees consistent state to its tables by adding a log file that records all the intended updates to your database tables. Any operations that potentially alter the database table must first be preceded with writing a record to the log file, and the actual update to the database table can be done only after the log records are completely written to the log file. During recovery of the database failure, the DBMS can decide whether to commit or revert the changes by comparing the state of your table with the recorded log file. Let's use this example when we try to transfer 500 from one account to the other. And assume the initial balance in A is 10,000, initial balance in B is 2,000. After the transfer, the expected balance in A should be 9,500 and the new balance in B should be 2,500. Prior to updating the tables, the database must first write 2 records in the log file. And let's assume that the format of each log entry is action, the target database, the target table, the old number, and the new number. So in our example, 2 records will look like update to table A, the initial balance of 10,000, the new balance of 9,500, and update to table B with the initial balance of 2,000 and the new balance of 2,500. During recovery of a failed operation, we can see one of the 4 possible states. The first state is when the balance in A is 9,500 and the balance in B is 2,000. If you compare the 2 numbers with the log entries, by comparing the expected value in A, we know that A's account is correct, but B's account is incorrect. So that means what we have to do is to update B's account from 2,000 to 2,500 and then delete the log records. And then the second possible state is when the balance in A is 10,000 and balance in B is 2,500. Again, by comparing the two numbers with the log entries, we know that A's account was not updated correctly. Then the action is just to update A's account and then delete the log. And the third state is when both accounts of A and B are not updated correctly. And again, by comparing the two values between the actual number in the table and the numbers in the log record, we know that we do have to update the two accounts to reflect the transfer. And the last state, the fourth state, is when everything goes well, you will see the balance in A is 9,500 and the balance in B is 2,500, which is the expected value, nothing went wrong, and we just delete the log. So using the log will help to recover the state of your tables to a consistent state. By borrowing ideas from database transaction, we can create a file system enhanced with journals. Before your file system makes any changes to its data block, superblock, or inode block, several records must first be written to the journal. The journal is just a log file. And the number of records will depend on how many targets in the file system will be altered, will be affected by the operation. Each journal entry will include a timestamp, the action, the block ID, the old content, and the new content. Journal file system has some benefits. So the first benefit is now it is possible for the user programs to wait shorter. Instead of waiting until the data are completely written, then the program can just wait until the log entries or the journal entries are completely written. So it doesn't have to wait until the actual data is written to the data blocks. But there's also a potential problem because the journal entries require a lot of space. If you look at the details of a journal entry, the journal entry has to include timestamp, the action, the block ID, the old content, and the new content. So the issue is with copying the old content, the new content, because this is like the content of the entire block. So depending on how the disk is formatted, the block size can go between 512 bytes to 4K bytes. So in total, the worst, the size of the log entry can be as high as 8K plus some numbers. To solve this idea, we can borrow a technique used by our animal friend. So if you remember the cow, copy on write, we can apply the same principle to our file system log entries. So using this policy, whenever a block is about to be altered, then the policy says don't alter the block but make a copy of the block. So using this idea, then the journal entry will shrink from a big number like 1K to 8K in size to only a few bytes. Using this idea, we don't have to copy the block content into our journal entry, but instead, we will include the data blocks as part of the journal entry itself. So if you compare the formats of the journal entries, without cow, we have to copy the content of the block and the updated content. And the size of that entry can be as high as 8K in size. But using copy on write, then we don't have to make a copy because the disk block themselves will be part of the journal entry. The journal entry using this technique is now very short. We just need to include the timestamp, the action, the old block ID, and the new block ID, because the new block ID will be the updated content of that block. The size of the journal entry will vary between 13 bytes to 25 bytes. In case you use 8 bytes for timestamp and block IDs, then the total size will be 25 bytes. So this page is an illustration what happened when a file is about to be altered by a write operation. And in a Linux file system, there's a superblock that will keep track of the list of free inode and the list of data blocks. And we know that each file in the Unix file system is associated with an inode, and we assume that the green blocks are the data blocks used by your file. So what happens when one of the data blocks is about to be altered? With copy and write, we are not going to alter these data blocks, but instead we are going to make a copy. So let's say that the first block is about to be altered and the rest will remain the same. So instead of altering this block, the file system will make a copy of this block and then change the content in the copied block. So the old content will stay here, but the new content will stay there. And of course, because now the data blocks making up the file is different, then the file system must also allocate a new inode. So the inode, a new inode is created, and the information from the old inode will be copied over, and the inode will point to the old data blocks which were not altered, and also point to the new block which is the altered content of the first block. And of course, the link from the block map and the data map must be updated as well. And at this point, the inode map will point to the new inode of your file, and the old content are still maintained in the block. So we have the old inode, the old data block, the new inode, and the new data block. But now your inode map will point to the new inode. And this old inode can be kept for a while in case you want to go back to that version, and you can still go back to that version. Or it can also be marked for lazy delete for future cleanup by the file system. So in summary, without cow, any update to your file system will in fact overwrite your current data blocks. But with cow, any updates to your file system is going to make a copy and then redirect the pointers to point to the new data blocks. So if you know some internal details of Git, this is what happened in Git. So when you remove a file, Git will never remove that file. And when you alter your file, when you modify one of your files, again, Git will keep the old content of that file and then will allocate a new copy for the modified content.